Our next speaker is Denis from the University of Oxford, who will be talking about wreath-like product groups and rigidity of the von Neumann algebras.
Thank you very much for the invitation and introduction. It's my pleasure to give a talk in this global event. So everything I'm going to talk about is joined with Ionut Chifan, Adrian in Ioana, and Denis Osin. Okay, so there are two main ingredients of my talk, as you can see from the title. The first one is von Neumann algebra, and the second one is wreath-like products. So I will start with the first one. Let me first recall the definition of von Neumann algebras. So our setup is G will be a countable group. And we denote by L2 of G the complex Hilbert space with G as an orthonormal basis. And then Gx on this space by multiplying every basic element from the left. In this case, we get the left regular representation. Okay. And by definition, the group von Neumann algebra is an algebra of bounded linear operators from L2 of G to itself, such that this bounded linear operator commutes with this left regular representation of G. Okay, so this is just some large set of operators. They form an algebra. And we observe here that there is a natural embedding from your group ring into this group von Neumann algebra. So every element of your group G, instead of having it multiply every basic element from the left, you can multiply every basic element from the right. You get the right regular representation. And in that, so this multiplication from the right is in fact a bounded linear operator. So you will, and also your multiplication from the right and from the left, they commute with each other. So you get an operator in a group von Neumann algebra. So you can, in this way, you can embed your group algebra into L of G. Okay, and let's take a look at some examples. Well, first, if G is finite, then there is nothing left in L of G. L of G will just be CG. So nothing interesting happened there. And the interesting case started from infinite groups. So let's say G is the simplest infinite group, say the infinite cyclic group. Then in this case, L2 of G can be identified with L2 of the closed interval 0, 1 via the Fourier transform. Well, every square summable function, for every square summable function, you can turn the function into a square summable series by computing the Fourier series, Fourier coefficients. And if you get a square summable series, you can multiply the series by e to some power. Then you add the things up, you get a square summable function. Okay, so this is the identification. So by this identification, we can identify L of G with L infinity functions. Okay, so we get a nice description of the group von Neumann algebra in this case. And in fact, this description carries over to any infinite abelian group. So for any such group, you will have L of G. It can be identified with the L infinity functions. Okay, and well, I want to also talk about some motivations why we are interested in this group von Neumann algebras. Well, to be honest, I am not a von Neumann algebra guy. I'm an outsider of the von Neumann algebras. So I will just talk about my understanding to those things and maybe some partial motivation is that we want to enlarge the group algebra so as to have nice properties. Oh, excuse me for a second. I'm so sorry. Okay, so I want to enlarge the group algebra so as to have properties similar to the range of integers. Well, you know that in general, the group algebra can be very far from this ring of integers. But well, if once you enlarge it to the group von Neumann algebra, the algebra behave nicer. For example, the ring of integers, it's a principal ideal domain. So you can define notion of dimension for finitely generated modules over integers. So those will be just finitely generated abelian groups. And for group von Neumann algebras, you can define the notion of von Neumann dimension. So in that way, you can you can have a nice dimension function. This allows you to introduce notions such as L2 Betti numbers and etc. Okay, so this is my understanding of group von Neumann algebras. And also, well, just like people study group algebras to understand properties of the group, people study group von Neumann algebras to understand. There are some people to study group von Neumann algebras in order to study the group. And once you notice this approach, then there is a natural question you will ask. So what's the extent, what's the limit of this approach? Okay, and then we are naturally led to the following definition. Group G is von Neumann rigid or W star super rigid if whenever there is another group H with the same group von Neumann algebra as the one of G, then one has an isomorphism between H and G as groups. So these are the groups whose von Neumann algebra remembers everything of your group. So you, in principle, in theory, you can, and by studying the von Neumann algebra to understand every property of your group. Okay, so these are the such kind of nice class of groups. And there are von Neumann rigid groups, and I will talk about this in the next few slides, but their construction is not straightforward. So before I talk about those positive examples, let me first mention negative examples. So this is the non-example. It will be the infinite abelian groups, as we mentioned that every one of those has the group von Neumann algebra isomorphic to the L infinity function. So they all have the same group von Neumann algebra. And this is an absence of rigidity. So any algebraic property of your infinite abelian group, such as having torsion or any other thing, is lost when passing to von Neumann algebras. Okay, all right. And so we want to find groups with the opposite property. And so our main problem is to find von Neumann rigid groups. And just like when you study an algebra, you look at the simple case. This is the case when your algebra is simple. And in this case, you also want to look at the von Neumann algebras, which is simple. So in other words, it is a factor. It has only the trivial center. So for any von Neumann algebra, the center is, well, always contain the complex number times the identity. But we are saying that your L of G is a factor means that it wouldn't contain anything else. Well, you just have C times the identity. And it turns out that there is equivalent characterization pure in terms of the property, algebraic property of your group. That is the infinite conjugacy property, or ICC. That means any non-trivial element of your group, if you look, say such an element is lowercase g, then the conjugacy class of this lowercase g is infinite. Well, for every such g except for the identity. In this case, we will say that your group G has the infinite conjugacy property. Your group G is ICC. We will say that, and in this case, L of G is a factor. And this is an if and only if condition. So for example, abelian groups wouldn't have this ICC property, but free groups have this ICC property. Non-abelian free groups have this ICC property. Okay, right. So, okay, so this is the ICC property. Next, we want to find the groups. Well, we want to find the groups which are von Neumann rigid, and the Conne's rigidity conjecture tells us how to find such groups, or at least a place to look for such examples. It says that if G and H are infinite ICC Kazhdan property T groups and they have isomorphic von Neumann algebras, then G and H are isomorphic as groups. Okay, so before I talk about how this conjecture tells us how to find von Neumann rigid groups, I would just first want to recall this notion of Kazhdan's property T and some example of it. So a group G has Kazhdan's property T if any unitary representation of G with almost invariant vectors has a truly non-zero invariant vector. So this is, in other words, this is saying that the only way you can have almost invariant vector is that you have a true invariant vector. So this, you can have almost invariant vectors in the most obvious and trivial way. Okay, so this is Kazhdan's property T, and typical examples are higher rank Lie groups and their lattices, say SP1N, the symplectic group for n greater than or equal to 2, SLNZ for n greater than or equal to 3, and automorphism groups of 3 groups for n of rank at least 5. Okay, so these are the typical examples of Kazhdan's property T. So how does this Kazhdan's property T comes into play? We didn't mention it in the last few slides. So the observation to make is the following. Well, first, infinite ICC amenable groups are very far from being von Neumann rigid. They all have the same von Neumann algebra. So this is the first observation. So amenable groups are very far from being rigid. And then next, Kazhdan's property T is a rough opposite to amenability. So every amenable group with property T is finite. So if you have an infinite group, then, well, these two things are mutually exclusive. And so you start to expect that maybe property T groups will expect some kind of rigidity. And there are some evidence of this. So if G and H are lattices of the symplectic groups SP1M and SP1N for M not equal to N, then they will not have the same von Neumann algebra. So this is saying, well, this is not saying that these G and H are von Neumann rigid. This is just saying that there are von Neumann algebras, remember from which Lie group these lattices come from. Okay, so this is some kind of a weak version of rigidity. Okay. All right. So, and well, these are the kind of like the part of the reasons why Conne formulated this rigidity conjecture. Okay. So how does this conjecture tells us a way to find von Neumann rigid groups? Well, the following result of Conne and Jones says that property T is an invariant of group von Neumann algebras. Oh, we have a question here. Can an amenable group have the same von Neumann algebra as a non-amenable group? I remember the answer is no, right? Well, I'm not 100% sure, but I remember the answer is no.
So there's a characterization of amenability in terms of von Neumann algebras.
Yeah, as far as I remember, but well, maybe I can double check and talk about this later. Yeah.
Thanks.
Sorry about that. Okay. So, all right. So property T is an invariant of group von Neumann algebras. Well, that's saying that if you have a group G with property T, and then you have another group H, which we don't know whether H has a property T or not, but you do know that H has the same von Neumann algebra as G, then H also has property T. Okay, so with this result, we can reformulate the Conne's rigidity conjecture as saying that infinite ICC property T groups are von Neumann rigid. So that's why this conjecture tells us how to find von Neumann rigid groups, because we can just look at all infinite ICC property T groups, and those will be our example. Well, if this conjecture is true. Well, of course, we don't know whether it is true or not. And in fact, there are no positive or negative examples known prior to our work. Well, if a conjecture is open, then of course we wouldn't know any negative examples of it. But interestingly and surprisingly, there are no known positive examples prior to our work. Well, usually you have a conjecture, you suspect that it is true, you will have tons of positive examples. Well, this is just not the case for this conjecture. That's kind of interesting. And So, but anyway, we are going to construct examples of this conjecture. And one ingredient we use a lot in our construction is the so-called wreath-like product, a generalization of wreath-product. So let me introduce the definition. G is a wreath-like product of groups A, B if it fits into an exact sequence of this form. So one goes to a huge direct sum of this group A this A sub B are all isomorphic to A. So those are just copies of your group A. So you get a huge direct sum, and this is a normal subgroup of your group G, and the quotient will be B, and okay, and such that the conjugation action of G on this huge direct sum permutes those direct summons in the following way. The direct summand A sub B conjugated by G, by an element G, is equal to the direct summand A sub epsilon of G times B. So epsilon of G is an element of your group B, right? So you get this left multiplication, and this is a direct summand. So you want these direct summands to be permuted in this specific way. And the set of all wreath-like products of groups A, B is denoted by WR A, B. So we have a class of groups, and the typical example is the restricted wreath product A with B. So for those restricted wreath product, instead of this set-wise equality, we want an equality that holds for individual elements. So there are more restrictions for those restricted wreath products. Okay. So this is the wreath-like product. So how does this kind of like generalized wreath product comes into play in studying von Neumann rigidity? This starts with the following results of Popper that says if G and H are infinite ICC property T groups, and if the von Neumann algebra of Z with G is isomorphic to that of Z with H, then G is isomorphic to H. Well, this is some kind of rigidity, but not quite a von Neumann rigidity, because we have here the isomorphism is between the von Neumann algebra of the wreath product instead of the von Neumann algebra of the group. But building on the technique of this result, building on the technique of this result, in a later paper, Ioana, Popper, and Wreath, they show that if G naught is any, well, they constructed the first class of von Neumann rigid groups. They constructed the first example of those rigid groups. Their construction is that if you have G naught a non-amenable group and S is any infinite amenable group, then the generalized with product of the form, first you form G with S, and then you form such a kind of generalized with product of this thing with Z mod 2Z, then this is von Neumann rigid. So these are all examples of von Neumann rigid groups. But if you compare these examples and the Conne's rigidity conjecture, then there is one ingredient missing. This is the property T. In fact, those groups would not have property T. So still finding a positive example is open. And the following is the main results of us. And it says that let A be a non-trivial abelian group and let B be an infinite ICC subgroup of a hyperbolic group. Then any wreath-like product G with property T is von Neumann rigid. Okay, so it's saying that some wreath-like product with property T is von Neumann rigid. And if you take a closer look at this statement, it's kind of weird, right? Kind of strange. It says that if I have a group which is a wreath-like product and with property T, then it is von Neumann rigid. It doesn't tell us whether such a group exists. Well, if it is the case that no such group exists, then of course any statement would be true for the trivial reason, of course. And so the question is, does such a group G exist? And this is where our group theory techniques or our techniques of geometric group theory comes into play. Okay, one way we constructed such groups is the following. So this is the, well, while this proposition. So let G be a torsion-free hyperbolic group, or more generally, and a cylindrically hyperbolic group without non-trivial finite radical, non-trivial finite normal subgroup. So a cylindrically hyperbolic group is a far-reaching generalization of hyperbolic group. And then the conclusion is you can find an infinite cyclic subgroup H of your group G such that the normal closure of H, well, denoted by this notation. This is the normal closure of H in G. This normal closure has this free product structure. It's the free product of conjugates of H by elements of some set T, where T is a set of left coset representatives of this normal closure in G. Well, so this statement is a bit long and takes time to digest. So I do want to provide an example. Let's say if I have my group G, a free group on two generators, A, B, and H is the subgroup generated by A. And in this case, we can take B to be the subgroup generated by B. And in this case, I will have the normal closure of H is the free product of A, or of the subgroup A, sorry. So this is the subgroup A instead of just the element A itself. Will be the subgroup A conjugated by different powers of B. So you take it. So this is kind of a well-known property of free groups. And in this result, we generalize these to torsion-free hyperbolic groups or to cylindrically hyperbolic groups. Okay. And the point is, of course, free groups does not have a property T. So we want to have the statement for hyperbolic groups. Okay. And then how this free product structure help us in finding the Wreath-like product with the desired property. Okay, sorry, before I talk about this, let me mention a bit how to find this subgroup H. And first, there are two steps. Well, first, there exists a hyperbolically embedded subgroup K, which is the free group on 7 generators by result of Neumann, Kazhdan, and Osin. So this hyperbolically embedded subgroup is kind of like a generalization of the free factor. So we first look at such groups, and then H is then a free factor of K. And then this free product structure, the equation 1 follows from a result of myself, which tells you when you have this kind of hyperbolically embedded subgroups, how to, well, under which condition you will get a free product, specific free product structure. Okay. Okay. This is how we find H. And once we find H, we can look at this short exact sequence. So one goes to this free product, and this is just the normal closure of H in G. And then you have this short exact sequence. And then we just small out everything here by the commutator of H. Then here I will get a large free abelian group, and then I will get something in the middle. And at the end, I didn't change anything because the commutator subgroup sits inside of the subgroup itself. And also the commutator subgroup here is a normal subgroup of G. So I can model out this commutator. And this, with this short exact sequence, with a bit more work, you can show that this group in the middle is the Wreath-like product of Z with G mod the normal closure of H. Okay. And so, well, then we get a lot of things from in the Wreath-like product. And the point is that if I start with group G with Kazhdan's property T, I start with a torsion-free hyperbolic group with Kazhdan's property T. It's well known that such group exists. Then, then this property T pass to the quotient. So my quotient will also have property T, and you can guarantee that all other desired properties of the theorem holds true. And then we will get the examples, and those will be von Neumann rigid by the theorem. Okay, so this is last thing I want to say. Thank you very much for your attention.
Okay, thank you very much for your talk. Does anyone have any questions? So I was still digesting your last slide. I will ask a question in a minute.
Yeah, so for last slide, there are some other properties we need to guarantee for the group. So for example, we need to guarantee that G mod H is hyperbolic, or at least a subgroup of a hyperbolic group. So there are still some properties we need to guarantee, but this is roughly idea. Yeah.
So, I mean, H is just some, so all you're doing really is quotienting out a single element, like the normal subgroup generated by a single element, and the kernel's got the specific for.
Yes. Well, there are generalizations of this technique. So instead of having this quotient of single elements, we can have more complicated things. So here it's kind of like the most the idea we start with, so to speak. Yeah, so this gives us some examples of well, those property T groups which are von Neumann rigids. And so for the question we are pursuing is that we want to modify these so that we want to construct uncountably many von Neumann rigid groups. So for that case, instead of having the Wreath-like product A, so just instead of having this Z, having this in this place, the abelian group, we need to have an amenable group. So we need to, so this is future direction. We are trying to modify this construction. Instead of having H here, we will look at, well, we will want H to be some kernel of some normal subgroup of hyperbolically embedded free subgroup such that the quotient is amenable. So there are some like freedom in modifying this technique, improving more things. So yeah.
Does G not have to be hyperbolic? Sorry, G over your quotient to apply this theorem?
You mean this quotient?
No, the one below.
The one below. Oh, you mean this one?
Yeah, does it have to be hyperbolic to apply your theorem?
Yes, so no, wait, no. To apply my theorem, we need to guarantee that this is hyperbolic. So let me go back a bit to the statement. It says that so this B is an infinite ICC subgroup of a hyperbolic group. So what we need to guarantee is that G mod the normal quotient of H is hyperbolic. So the way you do that is that first you have a hyperbolic group. So in this last slide, in this last slide, first you have a hyperbolic group G, right? And then you will find a free subgroup such that G is hyperbolic relative to that free subgroup. And then you Q a free factor. And in this case, you can get your quotient is hyperbolic relative to the trivial group or relative to a free subgroup. So this subgroup will be hyperbolic. Okay.
Okay.
So yeah.
Okay. Okay, sorry. Does anyone else have any questions? Okay, well, we should thank Ben Sun again. Thank you very much.
Thank you for your attention and for the nice questions.